So what am I supposed to? I guess it's supposed to be automatically on focus.
The focus should be automatic. Yeah.
But it's not completely focused, right? It was much more focused a minute ago.
Okay, I think we are streaming on YouTube. I just got it to stream on Sackless Strings, so I think we are streaming. It says you see a link above. If you go for the guys, for those of you who are on Zoom, you can see there's a link above, which is called YouTube. So
okay, is the blackboard in focus? What you see, Josef?
Tiny bit. Yeah, I can see it, but maybe a bit more in focus would not hurt.
Well, if anybody here,
I guess it's okay. I guess it's okay.
And can help me focus it, and
This is autofocus mode, so it's currently autofocusing. This is manual.
Yeah, you have to focus and then disable autofocus.
so I have to go to manual.
Then, yeah, you focus. When it's good, you stop focusing.
It's getting worse.
Now it's worse.
Yeah, it's okay.
Yeah, it's good now.
Okay. And you change now because
Okay.
when it is on autofocus, is refreshing.
Let me just adjust the focus a bit. Yeah. Okay. Now it's good.
No, it's good. Yeah.
Okay, let's start recording. This course by Jakub is our great postdoc who did his PhD in Prague and then went on to the first postdoc at ETH and then finally came here. And yeah, there'll be 3 lectures on string field theory. First lecture, obviously today. Second lecture Wednesday this week, and the third lecture is going to take place in 2 weeks on Monday. Without further ado, Jakub on string field theory. Anyway.
So many thanks, Damo, for the introduction, and also for the opportunity to take the course. So let me start by going through the rough plan of what I have in mind of telling you. Roughly, I was thinking originally about dividing the course into 3 parts, where in the first part, I wanted to tell you what SFT is and why we should think it is important to learn it. And yeah, then of course go through the basic details of constructing the string field theory action, starting from the free part of the action and then all the interactions, and then giving you examples, simple classical solutions. Then in part 2, usually in virtue string theory, we think about CFTs as tools. That is, we typically take a 2D CFT and use it to tell some interesting things, compute some observables in string theory. So now with string field theory, I will show you that we can actually also go the other way around, and we can use string theory to derive or to show some interesting results about 2D CFTs. So that was the plan for part 2. And then in part 3, I just wanted to give you a quick taste, quick gist of what has recently been happening in string field theory. But having said that, so let me confess that I would ideally like to go very slowly, especially over the first part, where I aim to give you some basic introduction to SFT. So that will probably have an effect that this part 1 of the course, I like to go very slowly and pedagogically, will spill over, fall into the second lecture. So that in effect will probably cause that there will not be much time left for this third part. So for the time being, I will put it in brackets. But at the same time, you can think of these applications of string field theory into the conformal field theory as very well as an integral part of the recent developments in SFT. So justice will be served in either way. So I hope this is it is much better to go slowly over the introduction without rushing rather than trying to go over it quickly. Yeah, do this part 3. So maybe in the future I can give some general thoughts about these. That said, let me start by going over a few resources which I found very useful in preparing these lectures, and which I hope you will also find useful when trying to learn more than I will try and tell you. So first of all, in general, there is this very nice and very recent review by Schrox and Barton's feedback. It came out last year, and really this is the I would say the most useful resource which I found for preparing this course. So then there is a book by Harold Urban about string field theory, which does not contain only string field theory. It also discusses in quite some detail the basics of the Birch formulation of string theory and also of gravity. So then finally, if you find yourself too busy to read this review, which has about 150 pages, or this book, which has about 300 pages, there is this very short review by Karel McAfee, which is only 30 pages. So that is very nice and concise. So then more specifically, for the string field theory describing closed strings, closed string field theory, there are these 4 lectures by that era, and also this a little bit longer review by Corinne de la Cura and company, which also discusses some applications of closed string field theory in string theory. So then finally, you're interested in some details about describing open strings and also open solutions. There is this very nice review again by that era. These are another 4 lectures, this time on analytic solutions in open string field theory. So now let me start with part 1 of the lectures. That is the introduction. First of all, let me try and give you some motivation as to what roughly string field theory is and why we should care about it. So I think it's correct to say that string field theory should be thought of as a quantum field theory or string theory. In the sense that SFT is in the same relation to string theory as the usual quantum field theory would be in relation to quantum mechanics for particles. We can also say that that this is an off-shell theory for strings. So in the usual kind of on-shell first quantized approach to string theory, what we usually start with is a Birch sigma model, which we quantize, right? We fix the reparameterization of symmetry. We can do so in many other ways. The way which I will choose later in the course is the BRST quantization. Where the end point of this procedure is a Birch conformal field theory, within which we can identify a particular class of states, which we call physical states. So then, in the worksheet approach to string theory, we can go directly from the physical states, following the usual prescription of computing some correlation functions on a Riemann surface and integrating these correlation functions over the moduli space of these Riemann surfaces to directly obtain on-shell string amplitudes. Now, the idea of string field theory is to go a little bit longer way. So, given the physical states, which should be roughly thought of as particles, to each of the physical state, we associate a string field. So this direction is going off shell. And as in the conventional quantum field theory for particles, these string fields should be thought of as living on the space-time, on the target on which the string propagates. So now, given these string fields, we will aim to formulate an action for these string fields. Will be the action for string field theory. And we will try and do so in such a way so that the Feynman rules given by the vertices of this action and the propagators will reproduce what we call off-shell amplitudes. So I will later in the course spend some time introducing these off-shell amplitudes, telling you what they are. So in particular, they should be thought of as generalizations of the on-shell amplitudes. So at this point, when we then restrict the external states to being back on shell, we should be able to recover the on-shell amplitudes, which we would have obtained by following this direct prescription of the worksheet string theory starting from physical states. So now, of course, you can ask the obvious question: why should we go this longer way? Why it is not enough to just start with the physical states without ever going off shell and compute all the observables which you like by just following the usual worksheet prescription? So now I will spend some time telling you many reasons why it is good to go this longer way, and why it is actually not always enough to follow this prescription of integrating over the moduli space. So first of all, let me start by telling you something which may sound a little bit provoking. And this is that this prescription may not always be well defined to give us finite answers where we expect to obtain finite answers. So in particular, there are many ambiguities with following this prescription, and many of them have a common denominator, which are IR divergences. So let me give you a couple of examples where these IR divergences arise. And to be very concrete and to stay at a very simple level of discussion, let me consider the simple cases of 2-to-2 sketch rings, that is, 4-point on-shell amplitudes. So even at tree level, one finds that this generic prescription for computing on-shell amplitudes generally only works when the external states are allowed to have generic momentum. So to give you an example, where we encounter an IR divergence at specific momenta, let me draw the following Riemann surface. So this Riemann surface is supposed to be a Riemann sphere with 4 punctures, at which I'm inserting on-shell states with momenta K1, K2, K3, and K4, which are on-shell. And this kind of a very, very thin neck in the middle is supposed to describe the Riemann surface near its degeneration, where the Riemann sphere becomes actually 2 Riemann spheres, which are connected by a very, very thin long tube. So this I schematically draw as such a pinching degeneration, but you can really think of this as being conformally equivalent to 2 Riemann spheres connected by a thin tube. So in this region of the moduli space of this 4-punctured sphere, this amplitude can be clearly represented by a Feynman diagram, where I have K1, K2, K3, K4 at the external x, and so on between K propagating in the middle. And for generic choices of K1, K2, K3, and K4, this propagator, this momentum K, and the propagator will be off-shell. So this is fine. But now, when there are massless particles in the theory, I can in principle choose one of the external momenta, let's say K4, to go to 0. So let's see what happens then. If K4 goes to 0, then by momentum conservation, K becomes equal to K3. But K3 is on-shell. And since we know that this propagator in the middle, I mean, in a completely generic theory, should go roughly as K4, so K squared over, 1 over K squared plus m squared. You see that in the case where K4 goes to 0, this propagator is forced on shell, and we obtain a divergence. But at the same time, we know that there are situations where we would exactly like to put one of the external states at 0 momentum. So these situations are precisely when we are trying to take the background which we are starting with and deform it by adding some marginal interaction to the action. Or the marginal interaction is precisely represented by the 0 momentum external state. So we know that the 0 momentum insertions we would like to interpret them as computing an amplitude. So in this case, it would be a 3-point amplitude, but on a background which is deformed by inserting a 0 momentum marginal state. And then, of course, we expect to obtain a finite answer. So this is not good, right? So we will see that in string field theory, we'll be able to exactly deal with such kind of situations, because in string field theory, we should be constructing the deformations of our background as classical solutions, So following that prescription, we will realize that around the different background, what we should actually do, we should rethink what our physical states is. So around the different background, we will see that the masses of the physical states will regenerate receive some corrections, which of course we naively didn't really assume here. So here we are trying to construct the amplitude around the different background using the physical states of the original undeformed background. So in SFT, you'll see that there will be an exact description of making sense of that computation of the amplitude around the different background in such a way so that we obtain a finite answer. Yes.
Are there backgrounds that I can't obtain by deforming around a given background? Is it a connected space?
Yes. So the solutions which we will have in mind and which I will construct explicitly later in the course, these are the solutions for marginal deformations. So they will depend on a continuous parameter. If the marginal deformation is not obstructed, if these moduli of the background do not receive some potential, right? So then the string field theory will be able to obtain a finite region for the moduli space around the point which we're expanding. So this was an example of an IR divergence which you would have obtained in the usual worksheet approach, even at tree level. But then when we go to the loop level, the situation gets even worse. So there you'll see that we can get IR divergences even at generic momentum. So for that, let me draw the following Cleveland surface. So this is again an amplitude of 4 on-shell closed strings. This time at 1 loop. So this is represented by this handle here. So again, this region here should be thought of as a very, very long thin tube where a closed string propagates. So you can see that this is to be associated with a Feynman diagram of the following form. Let's draw this a little bit longer. So now, at this point, you can see that for momentum conservation, the momentum which flows through this propagator is again K1, while the momentum here is again some generic K, which is given as K1 plus K2. So here, even at a generic on-shell momentum, you can see that this propagator, following this loop on the external leg, is forced to be on shell. So that again gives us an infinity. So again, we can ask ourselves why are we getting this infinity in the usual worksheet approach? And the reason is very similar actually to what I was describing before in the case of tree level. That is that we are naively trying to use the on-shell states which are on-shell classically as tree level to compute the loop amplitude. But using the usual intuition of compute theory, we know that when we try and go to loop level, the masses of states can get renormalized, right? So this is of course something which has to be taken into account also in string theory. Let me draw another unhappy face. So not only the masses, but also the wave functions can get renormalized. So we will see that when we have string field theory at our disposal, there will be again a well-defined prescription of dealing with this problem, which again, you can already guess if you know some basics of QFT. So we know that in QFT, what we would have done, starting from the classical action, what we would first do, we would formulate the 1pi effective action, and then of course we could construct the 1pi propagator. From the 1pi propagator, we could read off the poles of the renormalized states and also the residues of these poles, which would give us the wave function renormalization, and then using this renormalized spectrum, we could get finite answers from perturbation theory. So provided that we can get a quantum field theory formulation of string theory, we could just do the same and get finite answers. So now let me give you one more example of an infinity, which we cannot simply deal with using the first quantized on-shell worksheet prescription. And for that, I will draw the following Riemann circles. Again, I will have one handle, but this time all the on-shell insertions will be in this other part of the Riemann surface. So that you can interpret as a diagram with this tadpole in the middle, right? So again, the momentum here will be just k, but the momentum here will be 0. So then you can see that as soon as the theory contains massless particles, which of course can be at the same time on shell and have a 0 momentum, which of course in string theory you generally have massless particles, you will get an infinity. So, and again, you can ask yourself, why are you getting this infinity? Well, what is wrong with your logic? And the thing which goes wrong here is that if you have tadpoles in the theory, that means that that your vacuum, which was the true vacuum at tree level, is no longer a true vacuum at a quantum level. In other words, the classical vacuum through this tadpoles will receive quantum corrections. So to actually illustrate what I've just said, let me go back to a very simple example of the phi cubed theory. And this, at the same time, this will tell us how this problem can be resolved in a field theory language. So considering the phi cubed theory, you can start with the classical action and compute the 1pi effective action. So that will roughly look the same as the classical action. So we will have a kinetic term. But then through loop diagrams, we will also generate this tadpole term, which is linear in the scale of field phi, plus some corrections just phi squared. So taking this action and varying with respect to phi, we can obtain the classical, or in this case, actually 1pi equations of motion for this field phi. And what we will discover is that phi equals 0, which if we're naively thinking would be the vacuum at tree level, is no longer a classical solution to the equation of motion, right? So phi equals 0 is no longer a solution, precisely due to the appearance of this term, which is linear in phi. So then instead, in order to be able to make sense of perturbation theory in the usual sense, what we have to do we have to re-expand the action around something which is a classical solution to the 1PI equations of motion, which in this case amounts to expanding this field phi around this value minus 2c square root plus some corrections which will come due to these terms which are higher order in field phi. So this will be the new quantum corrected vacuum for the phi cubed plus some new fluctuation which I done with psi. And then when we do perturbation theory of psi, we should recover again finite results. So following the same logic as in this simple phi cubed example, if we look at the 1PI effective action for string field theory for generic backgrounds, what we should generically expect to obtain are these linear terms which arise at loop level. And the way of dealing with the resulting IR divergence is exactly the same. To find a classical solution of the 1PI equation of motion in string field theory, which identifies the correct vacuum around which we should perturb. So the IR divergences are certainly one good reason why to try and obtain a field theory action, or why to obtain a field theory formulation for string theory. Another good reason are the non-perturbative corrections to string amplitudes, which in string theory arise due to the so-called instantons. So as we know, the amplitudes are generally given by a path integral. So these path integrals they generally receive contributions not only from the perturbative regime, but also from settles from classical solutions which have finite on-shell action. So in particular in string theory, these settles with finite on-shell action, they are given by the branes, which have no non-compact Neumann directions, which are always the Dirichlet, which are not extended in non-compact space-time directions. So these d-branes we call the instantons, and there is a special case of the instanton, which is the d-1 brane, which is Neumann in all directions. So in general, some of the directions can be compactified. So if the d-brane is a Neumann object along this compactified direction, it will still have finite on-shell action, right? It will still have finite mass. So these in general will also contribute and will give corrections to the string amplitudes. And then there is also the special class which is Dirichlet in all directions, and these are just the d-1 branes. So in general, these will give us corrections of the order e to the minus a over g string to the Goldstring amplitudes, where a is precisely the value of the on-shell action. And the way how we would compute these contributions is, on top of considering the worksheets which are just Riemann surfaces with block punctures, which we do for the usual Goldstring perturbation theory. We also consider worksheets with boundaries. Where on these boundaries, we are choosing precisely the boundary conditions which correspond to these d instantons. So let me draw an example of such a surface. Again, this is going to be a Riemann surface with some genus in general. Punctures representing on-shelf closed-string insertions. And now, to represent the boundaries, I want to cut out some disk-like regions which will create holes in the surface of this Riemann surface. So these are the objects which we like to compute in order to obtain these de-instanton corrections. Now, if we will go and try and do so, we will discover that these amplitudes, they are really suffering from heavy IR divergences. Again, so again we have ubiquitous IR divergences. So to showcase how these IR divergences arise, let me consider a very simple example where we just have one boundary. So in the case of one boundary, and for the sake of simplicity, let me also consider zero genus, the Riemann surface becomes precise in the disk. So again, let me consider a special class of disks, a special region in the moduli space of punctured disks, where I have degeneration. So now this is a little bit different picture than I was drawing before. This thing is really supposed to be, let me draw it actually in the front cover. I've used blue for the boundary there, so let me also use blue for the boundary here. So this curve is supposed to represent the boundary of the disk. And this pinching degeneration here is now not to be associated with a propagating closed string, but with a propagating open string, because this is supposed to be conformally equivalent to a very thin strip of Hershey's. So this is now open string degeneration. But then you have to realize what the spectrum of open strings on a de-instanton is. And in particular, when it comes to the non-compact directions, since the de-instanton is supposed to be Dirichlet in the non-compact directions, it means that the spectrum can never support a finite momentum. All the states with respect to these non-compact directions, all the states in the spectrum, they have to be zero momentum, right? So as soon as there are massive states, which in general there are, right? Because the de-instanton typically has many moduli. In particular, in the non-compact direction, you can just shift the de-instanton any way you like, so that will generate a moduli space. So that means that there will be in general massless zero momentum open strings propagating in this channel, and that will again give us an infinity because the propagator will go up. So trying to compute these kind of contributions to the closed-string amplitude is using the usual Virchow prescription is doomed to fail. So then again, we can ask ourselves, I mean, in what way the string field theory can help us to perform this computation, and the answer is as follows. So as soon as we have a field theory formulation for this problem, we can choose to do the following prescription. We can choose to do the complete path integral computing this amplitude, except for the massless states which are supposed to propagate here in this channel. So first of all, what we compute is an amplitude is almost an amplitude, but without performing the path integral on the massless states, on the open string massless states which are propagating here. So that is, of course, supposed to be finite because as long as there are massive states propagating here, the answer is not going to be plagued by II divergences. But then, of course, in order to compute the amplitude, we're supposed to integrate over all the string fields, right? So what should we do? Now the key point here is to realize that these massless states, they are precisely in one-to-one correspondence with the moduli of the D instanton. So instead of performing the path integral over the massless fields, what we do, we will evaluate this amplitude, this disk amplitude, without performing the path integral over the massless fields at a fixed value in the moduli space of the D instanton, and then in the end, with a suitable measure, we can integrate over these moduli, and that should give us the correct answer. And using the correct description of string field theory, the answer turns out to be finite. And in a particular example, so for instance, type 2B string theory, where we know what the answer should look like, because we know that type 2B string theory should manifest the S-duality even at the level of the co-string amplitude. We can check that the answer which we get from string field theory is indeed correct and in line with these expectations.
In the string field theory picture, is S-duality not manifest until the final answer in general?
Yeah, so depends what you ask. I mean, if you ask about the string field theory action, yeah, that, I mean, at that level, the S-duality is not manifest. Yeah.
So is there, just to take a concrete example, in the past several years, we've been studying the structure of approaching integrands in string theory, finding various these modular graph forms and lots of nice SL2Z invariant functions and forms. Is there a string field theory way to find those functions that mean anything in string field theory?
Well, I wouldn't say there is an independent way of finding these results. I mean, of course, when you have your string field theory, you can draw Feynman diagrams. You can compute the amplitudes, and taking the external X to be on shell. I mean, you basically recover the same structure as you would have obtained from the first quantized prescription. Yeah, but all these all these subtleties with the II divergences, they kind of come automatically from the string field theory calculations. So that's the only advantage which you get over the first quantized description. But I wouldn't say there are any known independent insights as to giving these structures which you're describing.
I guess in particular because their structures the integrand. So.
Yes. It's just the integrand, yeah, which is not really like an invariant notion in string field theory. Yeah. Okay. Let's continue with giving you a couple of more reasons why to do SFT before actually introducing the action of SFT.
We ask whether some more conceptual question while you were here.
Sure.
So as you said, you're about to tell us soon will tell us the action.
Yes.
And motivated SFT is like QFT for strings.
Yes.
Now we know that many, possibly most QFTs don't have an action.
Yes.
Is this aspect of string field theory supposed to be the first step towards something bigger, or is it just the analogy quite extend that deeply?
Well, yeah, I mean, yeah. Having said that, I will give you an action for SFT, and actually that connects to what I'm going to talk about now. The action for SFT, although it is supposed to be so-called background independent, right? So as I will tell you, that basically means that given an SFT action around any given background, we should be able to see any other background by expanding around a classical solution. That background independence is far from manifest at the level of the action. So maybe maybe this is not the most fundamental formulation of the non-perturbative string theory which there exists. And having said that, right, if there are these backgrounds which you're describing, which cannot be described by an action, those backgrounds will most probably be somehow missed by this background independence prescription of SFT, right? Because if I say that I can obtain any other background by expanding the original background which I start with in a small fluctuation around the classical solution, that is saying that the background is described by an action, right? So if there is a background which cannot be described by an action, I will probably not be able to find it using it, in this way.
Yeah, that's connected to the previous question. So I guess I was wondering, like, if there's some independent principled proof that actually the space of solutions is connected, I would have been very surprised if the answer were yes.
There is a proof for open string field theory.
So like without string field theory, just the space of things the string theory is capable of describing, the space of solutions is somehow connected. So that all you need is an action. Sounds like there's no such proof of that deep statement, but so at least string field theory can reconstruct some of the backgrounds, and maybe not all.
Yeah, I think that's that would be like a careful way of phrasing what the string field theory trying to achieve. But still, that space of backgrounds may be very, very big and may very well contain backgrounds which we don't know about and which we wouldn't be able to discover using other methods, right? So precisely, let's talk about background independence. In this kind of restricted sense, which we were just discussing with Eric, so the situation in the first quantized Verchi string theory is that in order to be able to compute the amplitudes, we need to first fix a background. We first need to fix a consistent critical background for the propagating string. And then having fixed that background, what we can do is basically only to compute the observables for that fixed background. So in SFT, the situation is much richer than that. So let me just put down on the blackboard what I've been saying, and that is that classical solutions of string field theory should be thought of as other consistent string backgrounds. So to give you some examples, again going back to what I've already discussed to some extent, there are the marginal deformations. Which arise whenever the backgrounds around which I formulate my string field theory contain some moduli. So then what I can do, I can construct a family of classical solutions of string field theory, which will describe precisely the way I can move around the moduli space and thereby obtain some other related string backgrounds. Then I can construct other classical solutions, for instance, the ones which we usually call tachyon condensation. So that is just a fancy string theory name for what would have been relevant deformations of the Verchi CFT. So this is precisely how string theory where we can make sense of tachyon instabilities. So whenever I construct a string background which has a tachyon in its spectrum, that should be thought of as being a sign of that background being unstable, right? So then you can ask, what happens if I introduce a small perturbation in this unstable direction? I mean, what is the endpoint of the flow which I trigger in this way? So string theory is precisely well suited for addressing that question. You can precisely start perturbing the string theory action in that direction and see what kind of classical solution, what kind of RG fixed point of the worksheet CFD we flow through. So then, and then of course you can hope that whatever theory you land at, I mean that would be stable with no tachyonic instabilities, or it will not, and you will have to flow again and again, right? So yeah. So one thing which I would like to note is that what I've written here is that classical solutions of string theory should correspond to consistent string backgrounds. But no one tells you that these consistent string backgrounds should be associated with worksheet CFTs. And indeed, there is expected to be a huge class of consistent string backgrounds for which you cannot write down a worksheet CFT. So an example of that would be a background containing NS5 branes, or in general, some ADS5 cross S5 backgrounds with Raman flux, right? So that's a famous problem of trying to formulate something which would be a worksheet description in the background of non-zero Raman flux, right? So here you can immediately see a possible advantage of having a string field theory formulation at our disposal. So it may very well be the case that although these backgrounds which I have just talked about may not have a worksheet description themselves, it may very well be the case that they can be obtained as classical solutions of a string field theory which is formulated around a background which does have a worksheet description, right? So then this tells you that there could be an indirect way of extracting some interesting physics of these backgrounds with no worksheet description, and that is by starting with a background which does have a worksheet description, formulating a classical solution, then expanding in small fluctuations and doing perturbation theory around that classical solution, which is supposed to represent, let's say, a NS5 brane. So let me put that down. Background without a worksheet description. So in that case, for those backgrounds, of course, we do not know what to do at all in the usual first quantized worksheet setting. So we can try and represent them as SFT solutions. Around a background which does have a worksheet CFT description. And indeed, recently there has been a lot of progress in that direction. That was started in 2018 with a paper by Sheen, Scott Collier, and Minjacho. We're precisely trying to implement that idea of constructing or of describing physics of ADS5, which is 5 backgrounds with non-zero Raman flux at large ADS radius, starting from space in the RMS description. And even more recently, they have achieved a complete construction of the solution representing ADS5 process 5 from that space. So this is a work which is to appear very, very soon. By Windbrecher, Dragomida, Jaroslav Feindflug, and Shein. So we'll invite us to look out for that paper.
We'll see.
Yeah, well, you'll see, but yeah, in particular, they construct, I think, in principle, do all orders the deformation of the flat space in RNS, which constructs ADS5 process 5 at finite value of the radius. So yeah, I think that's the stage at which they currently are. But then their objective is to expand around that solution and compute some amplitudes to recover some Grasor amplitude in ADS5. Yeah, basically using flat space variables. Yes.
It's related to the IR divergence that you were discussing. So, you do certain particles, sort of know that these IR divergences, they exponentiate, and they are not relevant for observables. So, do you expect something the IR divergences?
Well, yeah, I'm not sure. As I was trying to describe, all the IR divergences which appear in the conventional string perturbation theory, they can be traced back to us doing something which is not entirely correct, right? Either to scattering states which are physical states at tree level and not taking that into account in normalization, etc., etc. So I think these are a little bit different kind of IR divergences, which are more connected to our ignorance than to something physical. Yeah, I think most, or at least some of them, they can be thought of actually as UV divergences on the worksheet, right? Yeah. I mean, when I say IR divergences here, what I mean, there are like IR divergences in space-time, right? But on the worksheet, you can, for instance, see that if I take this surface near to its degeneration, what that means is that I'm separating two punctures from the other two punctures, so that is as good as having a collision of these two punctures. So that would have been a UV divergence on the worksheet.
But here, like once you upper normalize those UV divergences, you don't need the next operators in the effective action. Say you go through fields, there's so we define it.
Right. So yeah, I mean, what do you do in the string field theory one, which is the same as what you would have done in QFT, right? So you have to compute the complete 1PI effective action, which I mean, will in general receive contributions from one loop, two loop, etc. So loop by loop, you have to consider, let's say, contributions to the mass renormalization, wave function renormalization, etc., to the vacuum shift. And if you do everything correctly, consistently, you should be able to obtain finite answers loop by loop.
So, for instance, like in the standard model, you don't have to introduce infinite conductors, right?
Yeah. Yeah, that's true. Yeah. Okay. Yeah. I have to think about what the best answer to this is. But yeah, I don't think this is suggesting that that 1PI effective action formulated from string field theory would not be renormalizable or something.
Background independence and moving in the space of choosing it. There's some implicit statement that you can integrate up the perturbation theory. Will this be clear when you write down the action, or does one have to work to prove that? It's a status event.
Sorry, can you repeat the last part of the?
If I make a marginal deformation and I work perturbatively, then
Yes.
yes, I can really move a little bit.
Yes.
Move more than a little bit? Is it clear that I can do a non-perturbative resummation of procedure and actually get to a bona fide new background? And what does that rely on in the structure of the action?
Yeah, that actually depends on the particular string field theory which you are considering. So in the case of the open string field theory, you'll see that we have a complete formulation of the action at our disposal, which in the bosonic case is just cubic. It's the written OSFT. So there, I think people have been trying to make statements about reasonability of the perturbation theory, and yeah, actually, what I found is that the answer also depends on the choice of gauge in which you are trying to construct a solution. So there are choices of gauge in which you can only in which SFT is capable of reaching on a finite region of the moduli space, but it's not able to reach an arbitrary point in the moduli space. But I think the state of the art is that people expect the SFT to be able to reach also finite distances from the background which you're starting.
I'm afraid I'm asking the same question as before, I guess.
Yes.
Is it possible that this is the same question, that there are parts of the space of solutions that one cannot actually access by way of integrating perturbation theory? That will transcend the use of the action and require something like resurgence from string field theory or whatever I should call that?
Yeah.
Sorry, if I understand it right. The space of we should make a distinction between the connectivity of the space of fields and the connectivity of the space of solutions, right? So of the equation motion. So if I understand right, the string field theory is certainly capable of describing classical solutions which are disconnected from the point where all the fields are set to zero,
Yes.
right?
Yes.
So
in a sense, the non-perturbable existence of some solutions which are disconnected has nothing to do with the question of summability of some perturbation series, right? You've got some equations of motion which you can solve if you find some point which is disconnected, and you cannot reach this by axial marginal deformation, but string field theory can describe this point. Is this understanding correct?
Yeah, that's true. Although I mean such solutions are very rare. I mean when it comes to actually analytically constructing these solutions. I mean many of these solutions have been constructed numerically. But then again you can ask a question if the numerical solution to the equations of motion, which is constructed by truncating the solution level by level, if it converges or not, right? But but then there are examples. So there is a famous example of the tachyon vacuum in open string field theory, which is a solution which is non-perturbative. It is not connected to phi equals 0, right? And at the same time, it was proved to be a good solution of SFT equations of motion.
Okay, so I guess the conclusion is that even if the space of consistent backgrounds of string theory is disconnected, this is not an obstruction for string field theory to be able to describe.
yeah, right. On the other hand, the promise here seemed to be that we could start with one background and go a long way. But then that's as you pointed out, a logically distinct question. Being able to enumerate the complete set of solutions to these equations. So it turned out that you didn't have to do that. You could just know a few of them and then some perturbation theory. But it sounds like to understand how much of the space you can access, well,
yeah,
we don't know the answer because we don't know how big the space is.
Right.
Okay. Yeah.
Shall we take a break?
Yeah, I think this is a good point because now I'm about to start the construction of the action.
So it's 11:07. Let's take like a 10-minute break. So let's meet again at 11:20.
Perfect. I'll keep the YouTube broadcasting active, so you guys maybe turn off the volume.
Anyway, for some weeks.
Welcome back.
Thanks. Yeah. California was like,
Hi guys, the YouTube is still on, so you know if you want to say something private, you know I can stop the YouTube and start again, or we can talk in some other room, or you can stop the microphone.
right, yours is last paper.
Okay, do I have control over the YouTube from here or?
No. I'm the one who needs to shut it down. But if I shut it down, I need to restart the broadcasting. So I'd much rather leave it on, if you don't mind.
You can just leave it on. It's fine.
So maybe I mean, but again, don't say anything bad about anybody because it goes online. So
Apparently I do have more control than I thought. If I can figure out how to do this.
so you can just mute the microphone, for example. Yeah, now it's muted. Perfect. Hi, Jacob. Can you start your audio?
Yep.
Okay, perfect.
Okay, I'm restarting the recording, Jakub, so you can start whenever you want.
So let me continue the lecture with constructing the action of string field theory. Let me actually start with constructing the action of free SFP. So that is just a kinetic term for the string fields. And so to streamline the discussion as soon as as much as possible to avoid complications, let me stay in the bosonic group. So of course, there are also formulations of string field theory for superstrings. There we have to deal with additional complications having to do with the distribution or picture changing operators and amplitudes, etc. So the starting point for us will be the BRST quantization over G sigma model. So WS will be just their sheet. So for that, we need to choose a consistent background on which the string propagates. And the main idea behind constructing the free action for the string field theory will be to identify the condition on a state in the worksheet CFT to be physical. With the equation of motion of the free SFT. That's one guiding principle. And the other guiding principle will be to think of the BRST, global symmetry of the worksheet action as being lifted to gauge symmetry of the SFT action. Which should be followed, as I was trying to explain, with each physical state, we should associate the string fields, and the action for that string field should be thought of as living in the target space, in the space-time in which the string propagates. So the action for SFT should be thought of as action on that target space, and we will see that the BRST symmetry under the sheet will translate into quote-unquote BRST gauge symmetry of the string field theory action. So just to illustrate with a simple example, in particular to illustrate this first point, we can just consider a free scalar. So in free scalar, we know that the on-shell condition k squared equals to minus m squared is equivalent. So the on-shell condition of this, which we impose on this free scalar particle, is equivalent to the corresponding field equation of motion of the free scalar field theory, which is just the Cohen-Gordon equation, which of course can be derived by varying the free action for a massive scalar. So exactly the same logic we will try to apply in the case of a string theory. So assuming that we've already been through this process of the RFC quantization of the worksheet, what we end up with is the gauge fixed worksheet theory where the gauge symmetry which we have fixed follows the reparameterization symmetry of the worksheet. Sorry, here. And this gauge fixed worksheet theory is just a CFT of the meta sector and a CFT of the corresponding Go system, which we introduced in order to fix this reparameterization symmetry. So when I write this like that strictly speaking applies to just to the Go string. If I want to describe also the open string, I have to consider Riemann surfaces with boundaries, and on those boundaries I have to impose some conformally consistent boundary conditions. So in that case, I'll be working with BCFEs. So we can also add this little B bracket where B stands for boundary. So the CFT measure can basically be whatever you like. I mean, in very simple examples, which one usually considers in a first course in string theory, the CFT measure is just a bunch of free bosons, which will describe compact or non-compact flat directions of the target space in which the string is propagating. But really, this can be anything, anything except for the fact that it has to have total center charge equal to 26, which is exactly to balance the center charge of this ghost CFT, which is just the usual BC Go system, which I will review in a moment. And that has a center charge of -26. So the total center charge on the worksheet.
Does it have to be unitary?
This thing?
Yeah.
No. Time-like free boson is not unitary. Can be random. So then, as I've just promised, let me recall few basic facts about the BC Go system. So that is a CFT which is actually given by an action. Not all CFTs actually can do that. The action is as follows: B del bar C plus B bar del C bar. Where B and C are fermionic fields with scaling dimensions 2 for B and scaling dimension -1 for C. As I was saying, these are Grassmann out. So then I can study some details about the CFT. Let me write down the mode expansions for these two fields. These are problems around series, which precisely reflect the scaling dimensions of the two fields. So from that, you can also read of the corresponding action of the modes on the SL2 C invariant vacuum, which in the case of the B modes, you can split the modes into creation and annihilation operators, where the modes annihilate the vacuum for m greater than -2, and in the case of the C modes, they annihilate the vacuum for m greater than +1. Again, reflecting the scaling dimensions of the two fields. So then, in order to be able to compute correlation functions in this CFT, you have to know what the OP of these two fields is. So the OP of BC is just 1 over Z minus W plus radial terms. From which it follows, and that can be translated into the mode language that the anti-commutator, which I will be writing as a graded commutator of the BNC. So I will never use the curly brackets for anti-commutator. I will always assume that I know what the Grassmannality of the modes is, and I will just write it as a commutator. Thinking this is great. Now, another useful piece of information is the 3-point function in this theory, which is the following. Which again can be translated into the language of modes. So computing the following overlap of the C modes, I can normalize it. So that is equal to +1. So in particular, one thing to notice is that in order for any correlator in the BC CFT to be non-zero, I need to require that at least at the level it has ghost number 3. So ghost number, that's an additional concept I want to introduce. Is a quantum number in the CFT, which is associated to a constant current, and it assigns value +1 to the C ghost and the value -1 to the B ghost. So that exactly as I was claiming, when I have 3 C ghosts, I have ghost number +3. And the associated conserved current, you can quickly verify this is just minus BC normal order. So then given these facts about the BC ghost CFT, we can write down some representatives of typical states in this combined matter ghost Birchie CFT. So these are the typical string states. So now let me separately go through the things of the open string Hilbert space and a ghost string Hilbert space. So in the case of open strings, I can write down a generic state in the Hilbert space as follows. I can act with some C ghost creation operators, some D ghost creation operators on some generic state in the boundary conformal field theory Hilbert space of matter. So this is a completely generic representative of this Hilbert space. And later we will see that it is very useful to assign a grading degree to these states, which in the case of open string states, I will just define to be the total ghost number +1. So this is for later. Now for the ghost strings, so this is open or closed. You could say, okay, so let's so while the open string states that are just from holomorphic part of the BC ghost CFT and the BCFT matter, which is itself just holomorphic. Then for the ghost string, let's just take 2 copies, holomorphic and anti-holomorphic, and that's that. But there is an additional complication. So first of all, let me just write down a naive representative. It's just doubling the number of degrees of freedom, basically. And now the state phi is generic state in CFT matter, primary or descendant, whatever. And similar to the open string case, we will assign a particular grading to these states. And for the closed string, that will be just the ghost number. With no +1. So now the additional structure or the additional constraint which I need to impose on the ghost string state is the double matching, which is reflected both at the level of the matter CFT as well as at the level of the ghost CFT. So the constraints are as follows. So I need to require that L0 minus, or L0 minus I define to be, okay, just the difference between L0 and L0 bar of the total worksheet CFT. So L0 is the zero mode of the stress energy tensor in the worksheet CFT of matter and ghost. So it's the sum of the zero modes of the stress energy tensor in the matter and the ghost. And this L0 minus, I need to require that it annihilates the closed string states. Not only that, I need to require an analogous condition also for the B0 minus, where B0 minus is defined analogously as L0 minus, but for the B ghost. So B0 minus is going to be just B0 minus B0 bar. So now these are representatives of generic states in the worksheet string theory Hilbert space. But then, of course, not all of these to be associated with physical string states. So in BRST quantization, the condition which we need to impose on these states in order for them to be associated with physical string states is formulated in terms of an object which is called BRST charge. Which again, I will write down separately for the open and closed case. In the open case, this is defined to be just the contour integral of a virtual current, which is called the BRST current. So JB is a field in the combined pair of the matter and ghost CFT, which can be written as the C ghost times the matter stress energy tensor plus the normal ordered product of B, C, del C. So then, similar as we are assigning some degrees or grades to the states and the Hilbert space, you can also assign degree, definite degree to operators acting on that Hilbert space. So this Q, that is an example of an operator which will act on these states. And in the case of operators, both in the closed and open case, you will say that the degree of an operator is exactly equal to its ghost number. So in the case of Q, you can read off that the ghost number is exact, that it's homogeneous in the ghost number and is equal to the +1, right? So here the +1 comes from the C ghost, and here the +1 comes from 2 minus 1, right? So then, in order to be able to do practical combination computations with this QO, let me also give you the values for form. decomposing it based on its content of B naught and C naught. So it can be written as B C naught L naught times B naught some operator M plus some operator Q hat, where L naught is just the zero mode of the total worksheet stress energy tensor. Now M is a certain combination of C ghosts, which can be explicitly written as follows. And Q is another combination of all modes and ghosts. Some space for that. So that's going to be equal to T minus N Ln, where these modes Ln, these are just the modes of the matter stress energy tensor. Plus minus a half sum over M minus N, C minus M, C minus B, and plus M. And the sum is taken over all Mn such that M and N are not equal to 0, and also M plus M. So that is an explicit expression for the BRST charge in the open string case. And then you can do some exercise with that if you like computations. For instance, you can prove that the condition that we're imposing, actually the only condition which we're imposing on the matter CFT so far, and that is that it has some charge 26, guarantees that this BRST charge is no potent. So you can try taking this expression for the BRST charge. You can try to square it. And what you find is that is equal to 0. Another useful property which will see you out in what is to follow, and which directly follows from this decomposition of the BRST charge, is that when I take an anticommutator of Q with B naught, what I will end up is just L naught. So that is very simple to see. So the only thing which this B naught sees is of course the C naught. That follows from this fundamental commutation relation in the BC goes CFT. The only non-trivial commutator of B naught is that with C naught. So when we anticommute this B naught with Q, the only thing which we detect is this first term.
Is that L naught matter or L naught of the whole?
That's L naught of the whole. That's total L naught. That's the L naught of the whole worksheet CFT. So now in the ghost case, the generalization is pretty straightforward. Instead of just taking a holomorphic combination of modes for the BRST charge, we define this to be some of the holomorphic sector, not the anti-holomorphic. And again, we could try and write down a similar decomposition as we did for the open case. By this time, it is already good to use the fact that we will only ever need to act with this QC of states which satisfy the Seba matching constraint. So using that, we find that we can actually write this as C naught plus, L naught plus, B naught plus, some M, and some Q hat. The operators with pluses are defined analogously to the operators with minuses, but replacing this minus with a plus. So C naught plus, for instance, would be actually 1/2 of C naught bar plus C naught bar, and B naught plus would be just B naught plus B naught bar without the half. So then again, we would have an analogous property to this equation in the open string case, and that is QC. I don't think I'm going to do mu plus this. So that's the BRST charge in both the open and closed case. So using this BRST charge, you can finally formulate the condition or the state in the rigid CFT to be associated with a physical state of a of a string. And following the usual BRST prescription, we are instructed to associate physical states to the BRST cohomology at a specific ghost number, which in the language of this grading, which I was introducing, turns out to be associated with degree +2 for both the open and closed string case. So this is one of the advantages of introducing this this degree instead of just working with the ghost number, because you see that if you were working with the ghost number, the cohomology would have to be specified at different ghost numbers for open and closed strings. Whereas if we work in terms of this degree, you can just say that it's degree +2 for both. So so this is as good as saying that a string state phi is physical if it belongs to the kernel of Q, modded out by the image of Q, which refers as a subset of the closed space as degree +2, and that in turn is as good as saying that phi is physical if and only if A, it is scaled by Q, B, we are instructed to identify physical states which are represented by phi, the physical state represented by phi, plus some state which is Q exact. So these two string states will be giving rise to the same physical state of the string. By lambda, well, we remember that Q had a degree +1, and in total phi has to have degree +2. So lambda is now any string state with degree +1. So now, before trying to implement this idea of associating the physical state condition with an equation of motion in string field theory, let me just quickly give you some typical representatives of physical states string theory. So for the sake of definiteness, let me focus on the open strings. So typically I can write down a state of the following form. So it's C1, V0 acting on the vacuum, where C1 is the +1 mode of the C ghost, and V0 is a field in the matter. Okay, to emphasize that it's in the matter sector, let me put this M in the brackets. It's a field in the matter sector which has scaling dimension +1, and it is a primary. So it's dimension 1 metric primary. So given everything I told you about BRST charge, you can act with the BRST charge on that state, and you can prove that it kills that guy. And in particular, if the CFT matter can be decomposed as a CFT of a bunch of free bosons, which are associated with some non-compact flat directions in which the string propagates. plus some CFT compact, which describes the rest of the target, which can be compactified, right? Then this V metric can take a particular form, right? We can write it down as some field phi, which belongs to this compact part of the matter CFT, times the plane wave in these non-compact free bosons. So that thing will be a matter primary as long as so that thing will actually will always be a matter primary. Then of course I can also consider some boson oscillators in front of this exponential. Then I would have to satisfy some additional conditions in order for that to be primary. But that is a very simple example of what would have been a matter primary, right? And it will be weight 0 as long as I satisfy the condition that the dimension of this field phi, which lives in the compact part of the Hilbert space, plus k squared, where k is the momentum of this plane wave, is equal to 1. So for states of that form, you can actually show, as I was telling you, that when you act with Q on that guy, you can pretty much immediately see that the action of Q in this case reduces to just acting with C naught L naught, where L naught is, since it is the zero mode of the total Birch stress energy tensor, it just measures the scaling dimension, which in the case of that particular state is k squared plus h pi minus 1, where this h pi is for the dimension of that field, and that minus 1 is for the dimension of this C1 C ghost mode. So this h phi minus 1 is what people usually call m squared, as the mass of the associated string states. So that allows you to rewrite the action of Q as just acting with k squared plus m squared. So then you can immediately see that that the requirement that Q kills the vacuum is as good as requiring that the momentum of this plane wave is put on shell. So this is how you make contact between this kind of abstract way of phrasing the on-shell condition with what you usually know, or what you usually encounter in theory here.
Statement that there's a basis for this Q cohomology which takes that form always?
Yes, I was just about to describe this. Actually, yes, with some caveats. I think the statement is true for open strings. For closed strings, there are examples of states, of physical states, which do not take this form and for which there is no representative of cohomology of that form. That is the ghost delta. I will talk about the ghost delta later in the course. But in general, what I can say is that the generic statement which we can say is that there always exists a representative of the cohomology, which is scaled by L naught, which is total worksheet conformal dimension 0. So in the open string case, we can say that it's scaled by L naught. In the closed string case, it will be scaled by L naught plus, right? And
can you remind what is L naught plus again? Can you remind?
So L naught plus is just L naught plus L naught bar. So it's an operator whose eigenvalues will be the scaling dimensions in the closed string. And the way to see this fact is as follows. So from this condition B, you can see that the cohomology is always defined, or the states in the cohomology are always defined after an addition of something BRST exact. And it's something which in detail in a moment try to interpret as kind of a gauge symmetry of the space-time SFT action. So in order to to do some practical computations, what we always do is we try and fix this freedom in adding NBR as the exact state. And what can be shown is that a consistent way of fixing this freedom, which can be always achieved by a suitable gauge transformation of that type, is to impose that the string states are killed by V naught in the open string case, or analogously with V naught plus in the closed string case. And that is called the Siegel gauge. So assuming that we are able to fix the Siegel gauge, you can then see that if we act with L naught on a representative optical homology which satisfies the Siegel gauge condition, we can expand this L naught as an anticommutator of Q and V naught. And then you see that one side of this anticommutator will kill this phi because phi is in the cohomology, it's Q closed, and the other side will kill because it's in Siegel gauge. So this is a way of seeing that that we can always find a representative of the homology which is in the kernel of L naught, which has total Hershey dimensions. So then let me come back to this original idea of implementing the physical state condition as an equation of motion. So the question is the following. Can we find an action? I will call it S3. Where these string states will enter as fields such that A, when we vary this action, this will impose the condition that Q and phi is equal to 0. And B, this action is invariant under the following field transformation, which just shifts the phi by something which is Q exact. So now the answer to this problem is the following. First of all, let me just, so as to speak, parameterize the answer by saying that it can be written in the following form. At the moment, we don't know what this omega is, well, what it is exactly in terms of some quantity on the worksheet, but I can tell you what its algebraic properties should be, so that this candidate for an action satisfies these two conditions. So omega should be a non-degenerate bilinear form on the string Hilbert space. Such that it's graded antisymmetric. So when we act with omega on some string states phi1 and phi2, that is the same as acting on phi2, phi1 with some sign, where the sign is just going to be given as -1 to the phi1, phi2. So here I'm using this shorthand. If I write phi1 and phi2 in an exponent of a -1, what I really mean is the degree of phi1 and degree of phi2. Okay, so it's like d of phi1 times d of phi2. So this is the graded antisymmetry. And the other property which I need to assume is that it's so to speak BRST invariant. So when I active Q on one of the insertions of this non-degenerate bilinear form, then again up to some signs, this is the same as acting on the other insertion. So now, given these algebraic properties, we can show that that they are enough to show that that this action which I wrote down on top of the board has these two properties. So let me just very quickly do that so that we can see that in detail. So for property A, what we want to do, we want to vary the action, right? So when we vary the action, we need to separately vary the first and second insertion into the bilinear form. So then let me focus on manipulating the second term. So in second term, what I can do first, I can use the second property, the BRST invariance, to rewrite it as minus omega Q phi P phi. So here I'm really picking up this minus, right? Because I have just this minus here, because when I move this Q past this state phi 1, I need to remember that that the string fields, which I'm using to construct physical states, they have degree +2. So this degree here is +2. So that -1 to the phi 1 contributes to the plus. So I just get this minus here. And then I can use the graded antisymmetry, that the first property of the symplectic form, rewrite it as d phi. So I've just said symplectic form instead of bilinear form. This is what this omega is sometimes called. So I will be using these two names interchangeably. So then you see that we have managed to massage the second term in precisely the same form as the first. So this plus half just becomes +1. So we get omega d phi Q phi. And if we impose that the variation is 0, then we can finally use the non-degeneracy of this bilinear form to show that this implies Q phi is 0. So that is this property A. Now for property B.
In this whole discussion, is phi a completely general state in the CFT matter plus CFT ghost?
So yeah, so okay, yeah, that's perhaps something which I should have emphasized. So at this point, we are just trying to build an action which reproduces the on-shell condition as an equation of motion, and we know that in on-shell the degree of that state which enters the on-shell condition should be +2. So in order to mimic that, I should have written this here. We should require that the degree of phi is +2. And it is something which we call the dynamic of string fields. But after that, it is a completely generic state in the string Hubble space. Yeah. By the way, while we are there, we can then also read what the degree of omega needs to be, right? Because we know that S should be just a number, right? Action is just a number. So then we can count phi is degree +2. This is also degree +2. Q is degree +1. So in total, we have degree +5. So the degree of omega is 3 minus 5. Okay. Now for this property B.
Sorry,
Yes.
I thought in the open string case at least that there's this +1 in definition of degree, so it's not clear the degree is additive if you multiply things. Like it is the ghost number which is additive, right? The degree has a +1, so
Yes.
so
it's
if
additive.
the ghost number is additive, then the degree is not additive because if you add two things together, you're gonna get +2 instead of +1.
Well, but then you see that the degree, I mean, was defined differently for the states and for the operators.
I see. Right, okay, yeah, got it.
So, so for this property B, we can already use much of the work which we done for proving property A. So this transformation Q lambda is in particular a very special case of a variation, right? So what we did here was for a completely generic variation of the action. So now we can substitute this special variation, right? But now for the special variation, which is supposed to represent the gauge transformation, we need to require that we actually obtain a zero for the generic phi, not just for phi which is in shell, right? So let's see how that goes. So now we can substitute for the lambda phi. Then again, we can use this BRST invariance property of the bilinear form, namely that if we act Q on one insertion, then this is as good as acting with the same Q, but on the other insertion up to a sign. So in this case, you can actually see that this is equivalent to lambda overlapped with Q squared phi. And then this is zero because we're assuming that our string background is critical. That is that the action charge squared 0. Okay. So this is how this definition of omega ensures that we can mimic these two properties with an action. So now, of course, I have to tell you if it is possible to define omega in terms of some worksheet CFD object. Of course, the answer is yes. And again, it will slightly differ between the open string case and the closed string case. So in the case of an open string, omega open acting on two generic states in the worksheet CFT, and we define as follows. So it is a certain correlator of the BCFT on the upper half plane, right? Where we know from the state operator correspondence of the CFT, we can take for any two states in the worksheet CFT phi1 and phi2, we can construct corresponding fields, which we can insert on the boundary of the upper half plane in the case of the open string. And what I need to tell you is what this conformal transformation I open is. This is the so-called BPZ dual, and it takes z, which is a coordinate on the upper half plane, to -1 over z. So this, I mean, if I tell you this, this should be, I mean, this you should compute any result of this binomial form for any two states, right? Just act with this conformal transformation on one of the insertions, and compute the corresponding two-point function on the other. And you can indeed prove that it has all the required properties which we listed above. In particular, for the BRST invariance, you can think of acting with Q on one of the insertions as inserting a contour integral of the BRST current wrapping one of the two insertions. And then by contour manipulation, you can see that this is equivalent as computing the corresponding correlation function where the contour integral wraps the other insertion. Okay, so by contour deformation, you can show that this bilinear form satisfies this BRST invariance property. Now for the ghost string,
Jakub?
yes,
Sorry. You said that phi 1 and phi 2, they live on the boundary of the upper half plane?
yes. So these are open string states.
Yes.
Yeah. So these are open string states, right? These are the states, I mean, which if I impose the BRST condition, I mean, they reduce to physical open string states, so they should be thought of as living on the boundary of the Riemann spaces, right? So in the closed case, there is a slight modification, which you can see that is necessary just by counting the ghosts. And that is instead of just acting with this conformal transformation on one of the states, you also need an additional insertion of C0 minus. And the reason for that is the following. So remember, the fundamental 3-point function of the BC ghost CFT was that the correlation function of free C ghost was non-vanishing and was equal up to some normalization to +1, right? So in the case of ghost strings, we of course need to have two copies, the homomorphic and anti-homomorphic coupling of the BC ghost CFT. So the corresponding non-zero correlation functions should be C minus 1, C minus 1 bar, C naught bar, C plus 1, C plus 1 bar. Where the C naught bar, you can quickly show that it can be written as C naught plus, C naught minus, to the minus sign. But then you have to realize one thing, right? You were requiring that that the states in the closed string Hilbert space are level matched. In particular, that is that they are always scaled by B0 minus, right? So if the states are always scaled by B0 minus, right, they can never ever contain an explicit C0 minus insertion. But that C0 minus insertion is always needed in order for any correlator of that type to be non-zero. So we need to supply an additional C0 minus insertion by hand. Otherwise, we would always get a 0. Is that kind of clear? Cool. So that's why the C0 minus insertion is needed. And indeed, you can count the degree or the ghost number. And since this guy contains 2 ghosts, this guy contains also 2 ghosts, right? Then we have 1 ghost from here. And then, for instance, an example of non-zero symplectic form or bilinear form would be when I insert a Q here. That would provide an additional ghost, right? So that correctly gives you the ghost number in order for that to be non-zero, right? So in principle, I mean, if these phi's are precise to the dynamical string fields, which have degree +2, this particular symplectic form would be always 0, right? But I can define it by canceling this restriction on the degree or the ghost number of the fields, and in that case, I mean, yeah, I could cook up states with arbitrary ghost numbers, so that this guy is non-zero. But what I can never ever restrict is the restriction that these states are level matched. I mean, this is fundamental to ghost string theory.
What you explained before is that everything is going to work as long as omega is like only going to be anything as long as antisymmetric and bilinear.
Yes.
So is there some uniqueness statement that this is the only choice?
Do
we have
maybe after some
other would it be some
similarity transformation is unique. So finally, just to finish at a nutshell points, let me quickly give you some very explicit examples of the kinetic terms which we construct in such a way for very specific backgrounds in string theory. So the background which I have in mind, which I will have in mind, is an open string background, and it's going to be the open strings on a D25, right? The D25 brain is an example of a boundary condition in an open string theory, which imposes Neumann conditions on all the directions. I will take it to be in flat space. So there, in constructing the explicit form of the kinetic term of SFT action, we can always use the fact, and this is something which you can prove very quickly, that the DRST charge commutes with the level operator, where by level, I mean the total level of the worksheet and ghost CFT, right? So in writing down the kinetic terms for string field theory, I can just proceed level by level without any mixing between individual levels. So it's diagonal in level. So starting with level -1, of course, what we all know that we encounter in bosonic string theory is the tachyon, right? So when we try and write down a state at ghost number +1, so at degree +2, so the open string. The only state which we find basically is the tachyon, which, I mean, if I assume that that all these Neumann directions giving rise to this D25 are non-compact, I can write down as a linear combination, as an integral over all possible momenta these open strings can have with some polarization, which will give rise to the space-time tachyon field, and then C1 with the IKX. So we can count the level. You can see that the only thing which contributes to the total level is just the C1, which is precisely at level -1, right? So this is a state at level -1, and the only state which you can write down at ghost number 1. Now at ghost number 0, it is at degree +1. You can think very, very hard, and what you will find that there is nothing. There is nothing which you can write down. So if you want to write down something which has ghost number 0, right, degree +1, then either there cannot be any ghost modes, or there has to be a certain number of B ghosts and C ghosts, right? But as soon as you try and introduce some B ghost, right, I mean, you find that you have to increase level, right? So the first non-trivial B ghost creation operator is B -2, right? So then if you want to compensate it to be at ghost number 0, you have to add a C ghost, right? But in order to be at level -1, you would have to add a C3, but C3 is an annihilation operator. So there is really no way of writing down anything at ghost number 0. And why I'm telling you this, so at ghost number 0, this is precisely the Hilbert space which would have given rise to the gauge parameters of the action. So this is telling you that there is no non-trivial gauge symmetry for the tachyon, which of course makes sense because tachyon is a scalar, right? So then, if you take the state phi at degree +1, sorry, +2, ghost number 1, and substitute it into the action phi p5, what you will find is precisely what you would have expected. So what you first do, you of course take these two states with two different integration variables, some k and k prime. You substitute, and what you find out is that by momentum conservation of k and k prime, you will obtain a delta function. So that delta function you can then use to get rid of one of these momenta, right? And then you can Fourier transform into position space. So then in the position space, you precisely find the expected action for massive scalar with an imaginary mass, that is with a negative mass squared. which is exactly what you would have expected from a time. So here I have written this in a suggested form for you to really appreciate that this minus box -1 is the position, should be thought of as the position space representation of this Q. But then, of course, assuming suitable follow-up conditions, you can always integrate this box by parts, and you can rewrite it in the usual form where you have del t minus d squared. So then finally, let me very quickly discuss a little bit less trivial example. And that is going to level 0 from level -1. So at level 0, things get a little bit more interesting. So again, starting at ghost number +1. This time you will find that you can actually write down two different states. So first, there's the state which will represent the gauge field. If there is just one brane in the stack, this will be just an abelian gauge field. If you choose multiple branes in the stack, things will become non-abelian, but let's keep this very simple and let's not introduce Chan pattern factors for the time being. So this is okay. So now you have to ensure that everything is at level 0. So on top of the C+1, we are also introducing these oscillators, which are the oscillators associated with the free boson CFT, representing the non-compact directions. And mu is the space-time index of the split target on which the string is propagating. Again, we have production on which this acts, inserted at 0. Now, on top of the states, you have also an additional possibility. And that is, instead of acting with C1, you can act with C0. So again, we have gotten something which is ghost number +1, or sorry, ghost number +1 and level 0. So now going to ghost number 0. So that is into the space which would contain all the gauge parameters of the theory. You will find that there is something non-trivial, as you would have expected, because the gauge theory, the theory of the gauge field on a brane, well, it should be a gauge theory, right? So we expect to obtain a non-trivial gauge parameter, which has the following form. So I'm using the normalization so that I obtain some familiar gauge transformation law. And now if you take this string field lambda and substitute it into this prescription for what the gauge transformation of the action should be. So you will substitute this lambda to the right-hand side, and at the same time, you will vary this phi on the left-hand side. That should tell you what the gauge variation of this A and of this B is. And you will find precisely what you would have expected, namely that the variation of this gauge field, provided that there is only one brane, is just del mu of this space-time gauge parameter with the lambda, right? Exactly as you would have expected in electrodynamics. But what you also find is that the gauge transformation of this B is the box of lambda. So now perhaps you start appreciating what the interpretation of this B is. It is precisely what we call the Nakanishi law. So that's the gauge transformation. And finally, you can take this phi and substitute this into the action omega phi p phi. And again, after some straightforward computation, what you recover is the following. Which does not look very familiar, perhaps, but you can do some additional manipulations, which will involve integrating by parts, assuming suitable flow conditions so that the boundary terms can be neglected, and also completing squares. And in the end, when the dust settles, you can rewrite it in the following form. From which you can read first that that this B field, this Nakanishi-Waltrip field, is really just an algebraic auxiliary field, which only has algebraic couplings in the action, no second derivatives, right? So you can complete squares like that, and you can see that the equation of motion for this B field is precisely this bracket equal to 0. So imposing this equation of motion, integrating out this auxiliary field, you recover the expected action for an abelian gauge field.
Sorry, Jakub, in the definition of the status phi,
Yes.
you have chosen the coefficients of the two terms to get exactly this equation, or how?
Yes. So I have chosen. Okay. Of course, I have chosen. I could have chosen the normalization. Sorry, right. So in that case, I would obtain different coefficients in this action. But then I mean that action would have been equivalent to would have been equivalent to what I've written down by a singular scale, right? So yeah, I think this is a good place to stop.
More questions for Jakub?
The original motion of Z will imply the Lorentz gauge.
Exactly. Yeah. So exactly. So okay. Okay. Yeah.
I mean, this is a consequence of the Siegel gauge choice, or maybe without the
It is.
choice.
It is connected to the Siegel gauge, and the precise statement is that at the level of this level 0 action, the Siegel gauge becomes equivalent to the Lorentz gauge, right? And you can immediately see that, right? You see that the term which is proportional to the B field exactly contains a C0, right? So if I require the Siegel gauge condition, that is that the field is killed by B0, right? That is as good as requiring that this B should be 0, right? Because the C0 is the only way of how I can make the action of B0 on phi being non-zero, right? So we can see that requiring Siegel gauge is as good as requiring that B equals to 0, which at the level of its equation of motion is precisely the same as requiring that the longer nu is equal to 0. So this is how the Siegel gauge for the U1 gauge field is equivalent to the Lorentz gauge.
No more questions? Let's thank Jakub again for the very nice lecture. And we'll see each other again on Wednesday.